In the cold, dark expanse of our solar system, beyond the asteroid belt, lie the giant planets. Some can be seen with the naked eye, others only glimpsed once by a passing probe. We are again sending cameras to the edge of the solar system to bring us new insights into the evolution of our worlds. Pioneer 10 and 11 made the first passage through the asteroid belt, leading the way for the venerable Voyager missions. These two probes made a grand tour of the outer solar system before slipping away into interstellar space. Jupiter, the first and greatest of the outer planets with its broiling sky, has had fleeting visits from other missions like Ulysses, Galileo and Cassini, each adding to the mosaic of Jupiter and its violent atmosphere.
My name is Amy Simon Miller, and I study the atmospheres of the Jovian planets. Weather on Jupiter is confined to a rather thin layer, kind of high up in the atmosphere. So the tops of the clouds are what we're seeing when we look at Jupiter. One thing we're seeing in the southern part of the equatorial region is little V-shaped clouds or chevrons, and we wanted to understand how those are moving in the atmosphere.
What we think chevrons are simply holes in the clouds. They are simply areas where we don't see any bright white clouds.
The Cassini mission flew by Jupiter in the year 2000, and because it was a slow, distant flyby, we got a lot of coverage of the planet over a long time period. So we were able to put those images together and make movies.
Using these movies, we observed Rossby waves that caused north-south meanders in a jet stream south of the equator. With new movies, we instead focused on hotspots. Hotspots are unique because we believe that there is a Rossby wave similar to what we previously detected, but instead of this Rossby wave moving north-south, it primarily moves up and down in the atmosphere. The downward portion of the wave pushes air down into warmer layers of the atmosphere. This causes any clouds that are embedded within the wave to evaporate and prevents further clouds from forming. So at any given time, there are approximately 8 to 10 hotspots in Jupiter's atmosphere that are spaced roughly evenly apart from one another. We believe that each of the downward portions of this Rossby wave corresponds to the hotspots that we see on Jupiter. This new finding is exciting because it'll allow us to re-examine the Galileo probe data and allow us to better understand it and better place it in the context of Jupiter's overall global climate and atmosphere.
The latest probe to be specifically aimed for Jupiter is JUNO. Launched 2011, the probe will reach Jupiter after a 5-year journey. JUNO's goal is to investigate Jupiter's interior structure and magnetosphere and help improve our understanding of the formation of the planet and therefore the history of our solar system.
JUNO spins like a propeller, where the propeller's kind of facing the sun because they're all solar powered.
If you spin something, it stays spinning. It's like a gyroscope. We can use a spinning spacecraft to let each instrument get its turn to see Jupiter. We get to go very close to the planet, inside the radiation belts instead of outside the radiation belt. We're in a polar orbit, so by small adjustments of the timing, we can map the entire planet. We can get repeated stripes at different longitudes as Jupiter spins underneath us.
It does mean that JUNO is going to see the polar regions to a greater extent than with other spacecraft. But I think the most important thing is that it gets in very close to the planet as part of that ellipse brings it in a few thousand miles above those cloud tops, very close, near the equator.
I think that's an interesting thing.
This one piece will make 52 layers.
Watch on mobile devices or the big screen, all for free. No subscription required.
We're going to go over the poles of Jupiter. That means we can study the magnetosphere in a different way.
A magnetosphere is the sphere of influence of a magnetic field. So a planet that has a magnetic field has a magnetosphere when its sphere of influence extends beyond the planet out into space and affects the region around it. The magnetosphere of Jupiter is vast. So if you think of Jupiter being 10 times the size of the Earth, and the magnetosphere is 100 times the size of Jupiter.
The JUNO probe is the furthest NASA has sent a solar-powered spacecraft. Sunlight provides 25 times less energy than on Earth, which means it requires advanced solar power technology with solar cells which are both 50% more efficient and more radiation tolerant than silicon cells. The craft also houses an electronics vault, which is radiation shielded to protect the electronics aboard from the intense and deadly radiation environment around Jupiter. The probe carries a full set of sensors: a microwave radiometer for atmospheric sounding and composition study, plasma and energetic particle detectors, a vector magnetometer, a radioplasma wave experiment and ultraviolet, and an infrared imager, plus a color camera called JUNOCam.
In Roman mythology, which of course is rooted from Greek mythology, Juno was the wife and sister goddess of Jupiter. And Jupiter was sort of being naughty with some friends, so he cast a veil of clouds around himself and his friends. But of course, Juno was a fairly powerful god herself and used her powers to look right through the clouds and see the true nature of Jupiter and understand what he was really up to. And that's exactly what the JUNO spacecraft does for us, is that it goes there with special instruments in a special orbit and uses its powers to see right through Jupiter's clouds and understand its true nature, which is holding these secrets for us about how the solar system formed and where we all came from.
A long-standing feature of the storms of Jupiter is the Great Red Spot. Large enough to swallow the Earth, this storm system has been studied since the 19th century. Then it was measured at a little over 41,000 kilometers on its long axis. Voyager 1 and 2 measured it at over 23,000 kilometers, and recent observations by the Hubble Space Telescope have the red spot at only 16,500 kilometers long. It seems the rate of shrinkage is increasing. One day it will probably vanish altogether. JUNO will also help confirm the theory that Jupiter was the first of the planets in the solar system to form from the primordial disk of dust and gas some 4.6 billion years ago.
I would expect JUNO to tell us more about how planets work, meaning how the heat gets out, what kinds of flows exist inside the body, how magnetic fields get generated. Learning what Jupiter is made of, we will learn such a wide range of things. For indeed, Jupiter is the most massive planet in the solar system. It is the body you want to understand in order to understand the architecture of everything else, including Earth.
Juno's year-long mission will end with a deorbit burn and a slow descent into the upper atmosphere, where it will continue to send back scientific data until its destruction. Perhaps the jewel of the solar system is Saturn, with her spectacular rings. All four of the outer planets have rings of ice and rock, but Saturn's is the most complicated, and, with thousands of ringlets, the most visible. There are several groups of rings classified A through to G. Some are formed by shepherd moons within the rings, and by gravitational tidal effects from others outside. Yet some gaps are still unexplained. The current spacecraft at Saturn is Cassini, on its second extended mission, the Cassini Solstice mission, which is expected to be completed in 2017. It continues to watch the planet-sized storms in the atmosphere.
Great white spots on Saturn are these large storms that erupt about once every year on Saturn. A year on Saturn is 29 Earth years. The great white spot that erupted in December 2010 initially presented itself as a small little white fluffy cloud that came up, and various instruments on Cassini were seeing it, and ground-based instruments seeing it as well. And as the days progressed, the storm got larger, and then it got sheared from the top and the bottom of the storm on either side of it, and it wrapped all the way across the planet. We'd never before been able to study a storm system of this magnitude in the infrared, so we are very fortunate at this time to have a spacecraft in orbit and excellent ground-based facilities, allowing us to make a historical record of this great white spot. And that will allow us to compare it in future generations when the next one happens.
Another phenomenon is a hexagon of clouds around the North Pole of Saturn, which has recently come into the light.
Cassini has been in orbit around Saturn for 9 years, and we've been following this hexagon which surrounds the North Pole. It's bigger than 2 Earths, and it's a wandering jet stream. But it's been winter in the north, so we have not been able to see what's at the center of the hexagon. But now it's spring, and what we found at the center of the hexagon is a Saturn hurricane. This is a view from directly over the North Pole, which is made possible by the orbit of the spacecraft, which is now taking us over the poles. The winds are flowing at 300 miles an hour, which is 4 times hurricane force. The fluffy white clouds in the center are about the size of Texas. We can use special filters to measure the heights of the clouds, and red are low clouds and the green are high clouds. We call it a Saturn hurricane because it has the eye, it has the high winds, but it's different from an Earth hurricane because it's locked to the North Pole. And unlike a terrestrial hurricane, there's no ocean underneath. And that's one of the puzzles we're trying to figure out.
A phenomenon first observed on Saturn by Pioneer 11 in 1979, and common to Earth as well, are polar auroras. These magnetic-generated light shows are far more spectacular on Saturn, rising hundreds of miles above the planet's poles. And unlike on Earth, where bright displays fizzle after only a few hours, auroras on Saturn can shine for days. Auroras are produced when speeding particles, accelerated by the sun's energy, collide with gases in a planet's atmosphere. The gases fluoresce, emitting flashes of light at different wavelengths. The Hubble Space Telescope has been watching them closely.
Starting in 2016, ending in 2017, these orbits will take us up and over the north and south poles of the planet.
We're actually going to dive in between the innermost edge of the D-ring and the upper atmosphere of the planet itself.
From that, we're going to learn how is Saturn constructed from inside out.
We'll also get the magnetic field of the planet, the mass of the rings for the very first time, and get to sample a place that no spacecraft has ever flown before.
This is a mission that cannot be duplicated. So we really want to take advantage of this opportunity to observe seasonal variation in the system.
Uranus has had only one visitor from Earth, Voyager 2. Like the other gas giants, Uranus has a ring system, a magnetosphere, and numerous moons. There the similarities end. Images from Voyager revealed a featureless atmosphere with no cloud patterns or storms. Uranus differs in its orientation as well. Tilted onto its side, its poles lie where other planets have their equators. Its magnetosphere is off-center and tilted as well, generating an unusual asymmetrical field. This causes Uranus's auroras to be well off the poles. Observations from Earth have shown seasonal change and increased weather activity as Uranus approached its equinox in 2007. The wind speeds on Uranus can reach 250 meters a second. Although there are currently no scheduled missions to Uranus, there have been several proposals put forward, both jointly from ESA and NASA and JPL, including both nuclear and solar-powered probes and an atmospheric descent probe. Ion propulsion is favoured because it allows a greater mass to be sent to the planet. Ideally, a probe could be launched in 2020 with a 13-year cruise to Uranus. As this is considered a low-priority mission, no funding has yet been allocated. The eighth and last planet in our solar system is Neptune, the last of the gas giants. Made of hydrogen and helium, it has trace amounts of methane, which gives the planet its beautiful blue color. It too has only been visited once by Voyager. The detailed images taken at that time revealed white clouds and a massive storm marring its atmosphere with supersonic winds.
The storm revolves around the planet every 18 hours. And then it rotates around its own axis like a big glob of pizza dough every 16 days.
Voyager also identified a ring system and confirmed 14 moons. Triton is its largest and is believed to have been captured by the planet from the outer Kuiper belt. Voyager also discovered Neptune's magnetic field was off-center and tilted, not unlike Uranus. Both Uranus and Neptune have had very little close-up study, and various missions have been proposed to fill the gap in our understanding of these ice giants. NASA has looked into several possible missions back to Neptune, perhaps a similar probe design to that of Cassini-Huygens, but due to fiscal and other constraints, none have been approved.
The Voyager mission to the outer planets has certainly been a journey of a lifetime. Having encountered Triton as the last world we would visit, I don't see how any of the scientists could have been happier.
Next stop was Pluto. When New Horizons was conceived, built and launched, Pluto was still a planet. The downgrade to dwarf made little difference to its investigation.
Well, you know, the key to planetary science is that you really have to go places to get the resolution, to get up close enough to really see what's going on. We want to get up close and personal.
New Horizons is the first really of a whole new breed of spacecraft that is focusing on a very specific task.
For this mission, the questions are basic. What do Pluto and Charon look like, and what are they made of?
We had to really be disciplined and say, we can't do everything. Let's focus on the primary questions and design the instruments to answer those primary questions.
New Horizons was built light and launched on a very powerful rocket, breaking all previous speed records when it left Earth on a solar escape trajectory at 16.26 kilometers per second. The spacecraft passed the orbit of the Moon in just 9 hours. It then cruised for just 1 year to reach Jupiter, where it was given a gravity boost, increasing its speed by 2 kilometers per second and cutting the travel time to Pluto by 3 years. New Horizons was the first to visit the dwarf planet and Charon, its largest moon. Pluto failed one of the 3 criteria to remain a fully fledged planet. It has not cleared the neighborhood around its orbit. Pluto is part of the Kuiper belt and not the only dwarf planet residing there. This is an image of Pluto at its closest approach. It still remains a treasure trove of scientific questions and hopefully answers about the origins and evolution of the solar system. From Pluto's flyby, it is on to the unknowns of the Kuiper belt. The most numerous objects in the solar system are the ice dwarf planets that make up this donut-shaped region on the edge of the solar system.
It's kind of like the asteroid belt, but much bigger. It has hundreds of times more objects in it than the asteroid belt.
The spacecraft will visit some of these objects in its travels.
Once you have the orbit, and we know where the spacecraft is and where it's going to be, we can figure out how much fuel the spacecraft is going to need to use to get to these objects.
After some careful calculations,
it looked like we might actually have to burn the engines to miss the object, which was a pretty exciting concept. You know, it's a good thing we looked, because you wouldn't want to run into one of these things.
These cold classicals, they're pretty much as they were 4.5 billion years ago. They're little fossils. That's incredible. We have no idea what they're going to look like.
New Horizons will continue to explore the outer solar system. There are many worlds within our solar system. Most reside beyond the asteroid belt. These are the moons of the gas giants of the solar system, each a unique and mysterious world of its own. Some have oceans of water, geysers of sulfur, or atmospheres of plastic. Some are just now being seen at the outer rim of our solar system. All are worthy of much more scrutiny. Currently en route to the Jupiter system is the scientific probe JUNO. It will be the first orbiter mission to Jupiter since the troubled Galileo spacecraft in 2003. Its task? to establish a highly elliptical polar orbit and study Jupiter in the greatest detail so far. Several other probes have made flybys of the system en route to other destinations. Some of these return fascinating data on the Jovian moons. Jupiter, the largest planet in our solar system, has, as far as can be ascertained, 67 orbiting satellites. Most of them are odd-shaped rocky masses, probably asteroids like AMALTHEA, trapped in the massive gravitational field of the planet. However, there are 4 major satellites of Jupiter, each large and dense enough to form spherical bodies. These are called the Galilean moons, named after the great Italian scientist and astronomer Galileo Galilei, who discovered them in 1610. Io is the smallest of the Jovian moons, though somewhat larger than our own moon and closest to orbit Jupiter. The intense gravitational effects causes the violent and active nature of the moon. It has over 400 volcanoes, lava flows, and plumes of sulfur 300 kilometers above the surface. The most dense of the 4 moons, Io is also the driest. Io is thought to be composed of mainly silicate rock with a molten core of iron or iron sulfide. Most of the surface is composed of extensive plains, coated with sulfur and sulfur dioxide frost. The surface is geologically young, which accounts for the lack of impact cratering. Unlike all the other planetary bodies, these craters have been covered over by volcanic activities. Numerous active volcanoes also eject material high above the moon and into orbit around Jupiter. The internal energy for this overactive moon is due to gravitational tidal forces between Jupiter and the other moons orbiting further out from Io. Just slightly smaller than our own moon, Europa has an icy crust covering what is believed to be a salty global ocean capable of sustaining indigenous life. It also has active geysers ejecting material into space.
So how do we think we know that Europa's ocean exists? Well, it's a combination of using telescopes on the ground and having spacecraft that have flown by Europa and collected data about the surface, about the interior structure, and about the magnetic field around Europa. And the combination of those data sets leads us to a high degree of confidence that this global liquid water H2O ocean is there today, and it's been there for much of the history of the solar system. And here's where Europa is a real game changer. It is far, far out from the sun, and yet it's got this liquid water ocean. And the reason that Europa has liquid water is because it's orbiting Jupiter, and the tidal tug and pull causes Europa to flex up and down, and all that tidal energy turns into mechanical energy, which turns into friction and heat that helps maintain this liquid water ocean beneath an icy shell. Along with helping maintain liquid water, we think that tidal energy may also allow that ocean to interact with rocks on Europa's seafloor. And it may even give rise to things like hydrothermal vents, which could help provide not just the building blocks for life, but also the energy for life.
Europa is the most likely place to find life in our solar system today, because we think there's a liquid water ocean beneath its surface. Now we know that on Earth, everywhere that there's water, we find life. So could Europa have the ingredients to support life?
we might be actually looking at a body that is presently alive, presently active, and presently undergoing its geology. There is too much evidence right now lying around on the surface, the red stuff, that suggests that something's going on there. Is that an environment that is habitable for any sort of life form? By golly, we really have got to go back and figure that out.
We have designed the Europa mission to take a spacecraft and its set of instruments all the way from planet Earth to Jupiter.
Previous mission concepts were for a spacecraft that would orbit Europa, but Europa is bathed in radiation from Jupiter. Any mission that goes in the vicinity of Europa is cooked pretty quickly. Instead, we're looking at a mission that will orbit Jupiter, make close flybys of Europa, and then zip out of the high radiation region. This allows us to have a mission that's many years long and to collect and transmit lots and lots of data. As Europa orbits Jupiter, it flexes, and we could measure the gravitational change of Europa by encountering Europa at different points in its orbit. On a typical flyby, we would turn on our remote sensing instruments, we would image the surface, we would interrogate the surface with spectroscopy, and we would do the same thing on the way out. And we would essentially rinse and repeat, and do this many, many times until we understand Europa globally.
Images from the Hubble Space Telescope tell us that Europa might be emitting plumes of water high into space. If so, a spacecraft could fly through those plumes and sample it directly to understand the composition of Europa's interior.
If it does have the ability to harbor life, how does that work exactly? We'll have enough instrumentation to really pinpoint exactly how the mechanisms would work for replenishing the nutrients in a subsurface ocean.
Europa is so important because we want to understand, are we alone in the cosmos? If there's life in Europa, it almost certainly was completely independent from the origin of life on Earth.
And for the first time in the history of humanity, we have the tools and technology and capability to potentially answer this question. And we know where to go to find it. Jupiter's ocean world, Europa.
The Europa Clipper mission has passed preliminary development and strategy proposals and acquired further funding. The European Space Agency has been invited to develop an additional probe to ride along with the Clipper, as with the Cassini-Huygens mission, and either land or impact on the Moon's surface. The nominal Europa Clipper mission would perform 45 flybys of Europa at altitudes varying from 2,700 to 25 kilometers. A proposed launch window would be in 2025. If launched with NASA's new SLS heavy lift rocket system, the probe would take less than 2 years to reach Jupiter. Otherwise, it will be a 6.5-year flight. The largest moon in the solar system, and another icy world, is Ganymede. Composed of silicate rock and water ice, the surface is heavily pockmarked by impact craters and regions of tectonic movement. The moon has a thin atmosphere of oxygen and possibly ozone and atomic hydrogen. The moon has a liquid iron-rich outer core and an internal ocean with possibly more water than Earth's oceans. Most recent modeling suggests the interior may be layers of water and ice, like a club sandwich. Ganymede is also the only moon known to have a magnetic field. However, it is embedded within the powerful Jupiter magnetic field and overwhelmed. But there are indications of auroral activity on the moon. Ganymede is also the final target for the Jupiter Icy Moon Explorer, or JUICE, the ESA-designated mission to 3 of the Jovian moons. It will be launched in 2022 from Europe's spaceport in Kourou, French Guiana, on an Ariane 5, arriving at Jupiter in 2030 to spend at least 3 years making detailed observations. It will visit Callisto, the most heavily cratered object in the solar system, and will twice fly by Europa. Callisto is the fourth and most distant of the Jovian moons from Jupiter, and outside the main radiation belt of that planet. Unlike its sister moons, Callisto has a very thin atmosphere of carbon dioxide and molecular oxygen, and low radiation exposure. Callisto is composed of silicate rock and water ice, and may also harbour a subsurface ocean. It is considered the most environmentally acceptable location for a manned base in the future. Saturn has 62 confirmed orbital satellites, many less than 50 kilometers in diameter. The bulk of the larger spherical moons are predominantly water ice and a small amount of rock. They include Mimas, Enceladus, Thetis, Dione, and Rhea. Enceladus is covered in ice with a subsurface ocean at the southern pole. Geologically active in the southern region, geysers have been observed. This would be from tidal heating and orbital resonance with Dione and Rhea, and could contain a liquid ocean heated by internal radioactive decay. However, the prize of the Saturnian system is undoubtedly Titan. Titan is the only moon with a dense atmosphere, and, other than Earth, the only body to have stable bodies of surface liquid. It is larger than both the planet Mercury and our own moon. Cassini deposited the probe Huygens on its surface in 2005.
Titan is Saturn's largest moon. It's actually the second largest moon in the solar system, and it's the only moon in the solar system that has a large and substantial atmosphere. And that atmosphere in some respects is really similar to that of the Earth, being composed mainly of nitrogen, but in other respects it's really different. It has methane as its second most abundant gas, and that takes the same role as water vapor in the Earth's atmosphere. It evaporates from the surface, it forms clouds, and then rains down again, and in fact forms lakes that we see at Titan's North Pole, including ethane and propane and all sorts of complex chemicals. We also see these vast dune fields at the equator, which are not made of silicates as they are on the Earth, but actually made of organic substances, essentially plastics, which have actually sedimented from the atmosphere and are being blown around into dune fields, the same as we'd see on a desert on the Earth. And through this we can detect which molecules are in the atmosphere. We see all the molecules that were previously discovered by Voyager. But we're also able to look for new molecules, and in fact, buried within the signatures of these more abundant molecular species, we saw a very small spike, which was due to a new species which had not been seen before. And in fact, this was propylene. So the discovery of propylene on Titan is really exciting. First of all, it completes this chemical family where we had this missing link dating 32 years back to Voyager. But also it shows that there's much more there still in Titan's atmosphere to be discovered. Some people think that Titan is similar to the prebiotic Earth long ago, when the molecules were forming the basis of life. And we don't know what we're going to find on Titan if we send back further spacecraft with new instruments, more sensitive instruments, if some of the molecules on Titan could be similar to the basis of life on Earth.
NASA is preparing a new probe to follow in Cassini's footsteps. It is called the Titan-Saturn System Mission.
Cassini was able to look at the lakes, get a sense of the coarse composition of the lakes, but nothing about the organic molecules that are dissolved in the lakes. The Titan-Saturn System Mission is a 3-in-1 mission with an orbiter for Titan, a balloon that will float through Titan's atmosphere, and a lander that will splash down on one of the northern lakes of Titan. This mission will actually go into a lake, sample the liquid directly, see what the organic molecules are that are present. The Titan-Saturn System Mission also will go to Enceladus, the tinier moon, 1,000 times smaller than Titan, which has volcanoes, geysers essentially, that are spewing material from the inside of this moon outward. And it's a chance to see whether there might be molecules that would indicate that life has actually formed within the source region of these geysers. These geysers have water ice, and we strongly suspect that there's liquid water in the region that these geysers are coming from. We know there are organic molecules there because they've been measured by Cassini. The ability to follow this up quickly is essential because with Cassini-Huygens, we have now trained a generation of scientists who are ready to take a new generation of instruments and capabilities back to Titan and Enceladus and really answer the questions that Cassini-Huygens has left for us. And that continuity of knowledge and of enthusiasm is essential and very difficult to maintain in the outer solar system because trip times are so long. The Titan-Saturn system mission really is Jules Verne realized. It's a kind of planetary exploration that we have never ever done before anywhere else in the solar system and can only be done on Titan. This mission will touch the human heart in terms of the way it's exploring this fascinating world. It will be floating on the surface of a lake. It will be floating through the atmosphere. It will be revealing the entire surface from orbit at the same time. As we think of exploration, of unveiling a new world, it's exploration in the true sense of the word.
The planet Uranus has 27 known moons, grouped in 3 categories: 13 inner moons, 5 major moons, and 9 irregulars. Only Voyager 2 has passed by these worlds. There remains much to learn. The major moons in order from the planet are Miranda, ARIEL, UMBRIEL, TITANIA, and OBERON. 4 of these moons have known internal processes such as volcanism and surface canyon formation. Miranda is the smallest of Uranus's round moons and one of the smallest objects in the solar system to be spherical under its own gravity. Strangely, it also has the tallest cliffs in the solar system. Thought to consist of equal parts of rock and ice, ARIEL's surface terrain, probably of ice, is cross-cut with canyons, scarps and ridges. UMBRIEL is again thought to consist of rock and ice. Its surface is the darkest of the moons and heavily cratered. The surface seems to have gone through some form of surface heating that destroyed its very early features. Titania is the largest of Uranus's moons. Similar in composition, heavy cratering has been obscured by changes to the surface through some heating event like its sister UMBRIEL. Titania may have a tenuous atmosphere as carbon dioxide and water ice have been detected on its surface. Oberon, the outermost of the spherical moons, seems similar to the others: ice and rock and heavily cratered. The surface has numerous scarps and graben from crustal movement. There are currently no plans to revisit these worlds. Neptune has 14 known moons, categorized into 2 groups, the regulars and the irregulars. The inner 7 moons orbit normally. The remaining half, including its largest moon Triton, orbit in either an eccentric, inclined, or retrograde motion. Triton orbits in the opposite direction to Neptune's spin. Scientists believe it was probably captured by Neptune's gravity in the early days of the solar system. Triton has an atmosphere that forms clouds and haze, and is the only moon closely observed by Voyager on its flyby of the system. However, Neptune plays a very important role at the edge of the solar system. The planets formed from a disk of dust surrounding our Sun billions of years ago. Remnants of this disk still remain: the rocky asteroid belt influenced by Jupiter and the icy debris cloud beyond Neptune.
Neptune creates a ring structure in the dust cloud which features a gap where the planet itself resides. And this gap should make it fairly easy to tell where Neptune is from afar, even at distances where the planet is too dim to detect directly. The supercomputer simulations that Mark Kushner and I performed also allow us to see what the dust in the solar system may have looked like when the solar system was much younger. In effect, we can go back in time and see how the distant view of the solar system may have changed. When we included collisions between dust particles, we were really amazed by what we saw. Dust collisions change Neptune's gravitational imprint. The gap in the ring structure disappears.
Over billions of years, Neptune shepherds the dust cloud into an outer ring to what is now called the Kuiper belt. The New Horizons spacecraft is exploring this region with its first flyby of the enigmatic Pluto and its moon CHARON. CHARON is the largest of Pluto's 5 moons. The other 4 orbit in erratic motion around the Pluto-CHARON pair. Nix and Hydra are both odd-shaped, contributing to their erratic orbital motions. This is Hydra, taken by New Horizons from a distance of nearly 650,000 kilometers, revealing its irregular shape. Pluto was the first of these trans-Neptunian objects detected and first thought to be a 9th planet.
And then Pluto was this kind of, odd guy out. It was this little object at the edge of the solar system. And then when we found all these other Kuiper belt objects, this is kind of almost a 3rd type of object.
So for the first time ever, we'll be able to fly by a brand new object, an object that's been forming for billions of years, and understand what outer parts of the solar system are all about.
Pluto is the first of the Kuiper belt objects, or KBOs, to be seen up close. There are many other KBOs, or dwarf planets, awaiting detailed scrutiny, such as Eris, almost the size of Mercury, and Quaoar, the first KBO discovered. The most eccentric orbit belongs to Senda, which has an elliptical orbit of 11,000 years, taking it to the icy Oort cloud at the edge of the solar system. The Oort cloud will one day become the new frontier.